In this video, we're going to derive one of three kinematic equations, and it can be seen in two different forms. The velocity as a function of time is equal to the initial velocity plus the acceleration times time, or many books write it as the final velocity is equal to the initial velocity plus the acceleration times a change in time. So we start our derivation with a definition of acceleration, and the acceleration is the first derivative of the velocity with respect to time. Now, with all of our kinematic equations, we work off the assumption that the acceleration is constant. So what I want to do first is separate my variables. I want to bring my dt over to the other side next to the acceleration, such that I'm left with a small infinitesimal change in velocity is equal to my constant acceleration times a very small change in time. Now I want to take the integral of both sides, and we remember that our acceleration is constant, so I can bring it out of my integral, and I'm just left with a dt. So if I take the integral both sides, I have that my velocity is equal to my constant acceleration times time plus some constant c. Now, when t is equal to 0, we know that we're just left with c, and we typically label this as v naught, some constant. So when I plug this back in, I'm left with the velocity as a function of time is equal to whatever my initial velocity was plus the acceleration times the time. And again, many books write this as v final equals v initial plus the acceleration times a change in time. Now we're going to continue our derivation of the kinematic equations right where we left off. And here I'm going to utilize the fact that velocity is the first derivative of the position with respect to time. Now when I plug this back in, I'm just going to be left with dx over dt. Now I'm going to use the same technique we used last time and separate my variables. So I'm going to multiply through by dt. This is going to leave me with dx is equal to v naught dt plus the acceleration times time times a very small change in time. So now I can integrate both sides. And what I need to recall is that the acceleration is a constant, as well as my initial condition, my initial velocity. So those can come out of my integral. So when I'm looking at this, I should have that the position, which is a function of time, that's evaluating my dx, is equal to v naught integral of dt plus the acceleration integral of time times a very small change in time. So now I want to evaluate my right hand side to give me v naught t plus 1/2 the acceleration times time squared plus a constant. What is this constant? Well, this constant again is going to be whatever the initial condition is for my position, and we label this as x naught. Plugging this back in, I get my equation of x as a function of time is equal to my initial position plus my initial velocity times time plus 1/2 the acceleration times time squared. Now, some books write this a little differently, and they write this as x final. Where I end up is equal to where I started, x initial, plus my initial velocity, the elapsed time delta t plus 1/2 my acceleration times the elapsed time delta t squared. And this is my next kinematic equation. Now we're going to continue our derivation of the kinematic equations by going back to the fact that the acceleration is equal to the first derivative of the velocity with respect to time. Now I'm going to use the chain rule, multiply the top and bottom by 1 by saying let's take the derivative of velocity with respect to position, and then let's take the derivative of position with respect to time. Now, what do we notice? This term right here, the derivative of position with respect to time, is the velocity. So let's plug that in. I can get 1 over dx, a small change in position, the velocity times a small change in the velocity. And again, the acceleration is always constant when doing our derivation of the kinematic equations. So let's separate our variables. Let's bring dx over, and I end up with the velocity times a small change, and the velocity is equal to the acceleration times a small change in the position. Now I want to integrate both sides. Again, the acceleration is constant, so I can bring that out of my integral. And when I look at this, I can then say, well, this will give me 1/2 the velocity squared is equal to the acceleration times whatever my change in my position was. So now if I'm looking at this, I also have to have my plus c, and I can solve for the velocity as a function of position squared to be 2a, the distance traveled, plus 2c. What is this 2c? Again, we use the same technique we did before. Velocity of position as at 0 squared is going to give me 2c, and we will just simply call this the initial velocity squared. Plugging this back in, I'm left with the velocity squared as a function of position is equal to what was my initial velocity squared plus 2 times acceleration times the distance traveled. Now many books write this again in a different form, and we'll say, well, this is the final velocity squared, this is the initial velocity squared, plus 2 times the acceleration times the change in the position. This is another one of our kinematic equations.